Okay, so good morning, everyone. Welcome to the Center for Theoretical and Computational Physics weekly seminar. It's a pleasure to welcome Doug Cleaver from Sheffield Hallam University in the UK. Doug and I have known each other for a long time. We first met in Southampton, where I was a PhD student and he was a postdoc shortly after his PhD, which he completed with Mike Allen at Bristol. So after his time at Southampton, Doug moved to Sheffield Hallam University, where he's steadily risen through the ranks and is now professor in the Materials and Engineering Research Institute. And well, we've done extensive work and published several papers and held several grants together. And we're still planning on doing more joint work now and in the future. And today he'll be telling you about some of his work on emergent symmetries in soft matter systems. So I'm going to give the baton on to Doug, but before that, can I just remind you to all except the speaker, please mute your microphones and switch off your cameras so as not to overload the internet and ensure best reproduction for all. So, Doug, the stage is yours.
Thanks very much, Paolo. Yes, very sorry not to be with you in Lisbon. I've given a few talks in your department over the years, and it was a real disappointment not to be able to visit your wonderful city this summer just past. We hope that European Liquid Crystal Conference can happen. So today I'm going to talk about liquid crystals and self-assembling systems, and with a general theme of emergent and disappearing symmetries in soft matter systems, and how we might characterize that and look at supramolecular order that comes in. I'll start off with something a little bit confrontational. Conventional wisdom, particularly in simulations, is that you only get out what you put in. And the outcomes of a simulation are usually pretty obvious if you sit back and look at it. And if you're missing something from your simulated system, then stick in the right kind of interaction in a really rather forceful way, and you'll get the result or the behavior that you're after. I'm going to try and convince you that's not always the case in the operation of this talk. Here's an example actually from theory. How do you get chirality into a system? How do you get some twist into a system? Well, obviously you put in some chiral molecules if you're doing an experiment, or you put in some chiral particles if you're doing a simulation. That isn't the case. It's not necessary to put chiral sites, chiral molecules into a system in order to get gross chirality. And here's a theoretical reason why, and this comes from quite an old paper, but a very neat little paper from Randy Kenyon. Consider the flexible thread on the left. It's sitting in solution and it's sitting fairly straight, but it is flexible. If you were to move, add some spherical colloids to that colloidal thread, say, and because of the depletion interaction, and you get a sufficiently high concentration of spheres, then in order to free up the lots of volume for those dark green spheres, you want the light green excluded volume region around the thread to shrink, and it can do that by having that thread coil like an old style telephone cable. It could coil left-handed, it can coil right-handed, but it will coil, and you'll adopt a net chirality, even though there's certainly no chiral particles or chiral interactions in the system. It's a lower free energy state is the coiled arrangement. So what I'm going to try and do today is to show you some disappearing and some emergent symmetries in liquid crystalline and self-assembling systems that we've found over several years, doing simulations in my group, But in preparing for this talk, I noticed that a few weeks ago you had a talk on this system, and this is a really nice experimental example from Roldulan's. He talked to you about using colloidal banana-shaped particles. Those colloidal banana-shaped particles, they're achieved by partially cross-linking SU8 colloidal rods. They give, well, he calls them bananas. I wouldn't call them bananas because they're not tapered. A real banana is thinner at the ends, and whereas these, I think, have got uniform cross-section. So when you stack his bananas, you wouldn't get anything happening in the third dimension. We don't get anything happening in the third dimension as you would if it was a stacked real bananas, or a hand of bananas has got a curvature going the other way as well. But with these SU8 colloidal rods, you got when baking these partially cross-linked things, then out came the splay bend nematic phase. These biaxial particles gave a uniaxial phase, but with this this additional periodicity going on. And in fact, it's a biaxial phase because you have the long axis of the nematic director, but you then have the bananas all lying effectively in plane with each other, so that their middle axes, or the axes that, around which they're curved, are all in the same plane as each other. In the splay bend nematic, the biaxiality of the particles is apparent in the phase, if you want to characterize this thing as a phase. In other concentrations or other curvatures, you just have the normal nematic, and that biaxiality of the particles is lost. So the symmetry of the object and the symmetry of the phase are not always the same, not necessarily the same. Actually, I wouldn't really characterize the bananas as being biaxial. I'd say they're polar, because they've got a clear polarity. They've got a long axis, but orthogonal to that, there's a clear polar axis. And they're not the symmetry of a book, the symmetry of a polar object. Okay, so I do molecular simulations and coarse grain simulations. I tend to do this kind of approximation where rather than simulating the full atomistic model, we'll approximate that with an ellipsoid of some sort. We'll usually put a 612 potential on it, at which point it becomes, rather than an ellipsoid, becomes what we call a Gay-Byrne model. And the conventional Gay-Byrne model, if you compress these soft ellipsoids, or you cool them down, you go from isotropic into nematic and into smectic beer, and this is very well characterized behavior. If rather than just simplifying a single 5CB like liquid crystal into a single ellipsoid, we want to get a single particle potential to mimic the behavior of something more exotic, like say a zigzag-shaped molecule. That zigzag-shaped molecule we could approximate as 3 ellipsoids. The interaction potential for those 3 ellipsoids would look something like this, with a long, thin, rigid core, but the attractive well would have minima shifted slightly up in this biaxial plane on the right-hand side and slightly down here, and there would be imagine a waist, like a rubber ring, if you like, going around the waist of this object, which links these so that the potential minimum follows a bit of a diagonal path if we were to go around. Want to mimic that with a single particle, then rather than the normal Gay-Byrne interaction potential, which looks like this, we shift the waist that's that represents the potential minimum for this thing, like this, then we end up with a potential which mimics this 3-sided object. And we can then look at the phase behavior of these objects, which have got a uniaxial core, but they are actually biaxial because of what we've because of the distortions we've applied to the well depth function. And sure enough, if we simulate these things with delta equals 0, we have the conventional Gay-Byrne interaction with isotropic nematic smectic behaviors and no biaxiality. But if we got a significant twist of the soft attractive potential with respect to the hard axis, then we get different behavior happening at low temperatures, we get a bit of a jump in the nematic order parameter, and we get a clear growth in the biaxial order parameter shown on the right. And what's happening here is that we've achieved a tilted smectic phase. The tilted smectic phase has come in because of that biaxiality in the soft interactions. And in fact, all the particles are leaning in a concerted direction, and each one is leaning towards the vertex of the hexagon. So what's happened here, I've put biaxiality and a molecular level tilt into the potential, and out has come a biaxial tilted smectic phase. So this is an absolute example of what you put in is what you get out, or what you get out is what you put in. We achieve the tilt at the phase level by putting in tilt at the molecular level. Now I'm going to try and achieve different things. I'm going to try and put things in, put symmetries in, and not get those same symmetries out, or I'm going to put in no symmetries and I'm going to get some surprising symmetries to come out. So yes, this is not a mistake. I'm deliberately showing a very similar slide to one a couple ago. This approximation representing 5CB as an ellipsoid is something that has been done for decades on Saga, Frenkel, Mike Hallam. Everyone's represented liquid crystals as uniaxial objects. But liquid crystal molecules are very rarely uniaxial. They almost always have a head and a tail. The justification for representing the liquid crystals as uniaxial objects really comes from the symmetries of the phases that they form. The nematic phase doesn't have a head, so it must be okay, therefore, to ignore the fact that the molecules have got heads and tails. Is that really a good thing to do? Are we actually throwing something away by making this head-tail approximation? What would happen if we simulated, rather than symmetrical ellipsoids, things which had clear heads and tails to them? Well, we can do that. So by, instead of simulating ellipsoids, squeezing one end and letting the other end bulge out, which sends back to having a pear-shaped object. What does that do? Low temperature is low concentration, it's isotropic. Compress it down and it becomes nematic. Compress it down a bit more and you get layered phases with the pointy ends interdigitating. You get bilayers. These are hard particles. Hard ellipsoids do not form a smectic phase. Hard pairs do. So by bringing into account the fact that heads and tails can be different from each other, we actually introduce additional phase behavior. No polar phases, but still additional phases, which only are there because the particles are polar. In fact, hard pairs do something else as well. Depending on the cone angle that you apply to the pair, there's a region of polar angles where you do not get a nematic phase. On compression, so on the right, we've got things which are only slightly distorted from hard ellipsoids, and they go from an isotropic phase into a nematic phase and into a smectic. But for a range of cone angles, which are a bit sharper than that, rather than forming a nematic, these hard particles go into a gyroid phase. Gyroid phase is a bicontinuous arrangement with an overall orientational order parameter of 0. They are orientationally isotropic. Again, this only happens if you have tapered particles. These particles are really rather interesting. They're actually the shortest, I think, the shortest hard particles to give smectic behavior. Spherocylinders, in order to form a smectic, you need an aspect ratio of 4.6 to 1. Here we straightforwardly see smectic behavior for 3 to 1 particles, 3 to 1 hard particles, and possibly even shorter than that. Plus, they show a really quite large gyroid region in the density versus cone angle phase space. This is what the gyroid looks like. So this is a snapshot of partial configuration when we revisit this work. This has been done by Philip Schoenhofer, who is now in Michigan with Sharon Klotzer. This is a single configuration. All we've done is change the color scheme. And if we show colors by orientation, then it looks like a really messy isotropic phase. But if we then do a color scheme based on close separations between the blunt ends of the particles, you can see two subspaces, two subsystems. These are picking out the two subnets involved in the gyroid phase. We can grow the gyroid in from low density, and if we know what the final arrangement of the gyroid is going to be, which is a subnet in which you have junction points, and each junction point has got 3 branches coming off it. We know which periodicity to look for. We look for clusters of that type of arrangement in terms of the blunt ends of the pairs. We can see lots of clusters forming at low densities. The different colors represent different clusters. But as we approach the density at which we know that the gyroid phase comes in, at about a row of 1.0 in these units, then rather than having lots of colors, we get the picture in the bottom right where we have 2 interconnected subnetworks of fully bicontinuous arrangement, where I can walk around in the light blue space or I can walk around in the dark blue space, and I won't meet myself yet. There are other bicontinuous phases. This is theoretical work from Gert Schröder-Türk. The gyroid is represented on the right-hand side, where the junctions have each got 3 branches coming off them. You can also have a diamond alternative where you have 4 bonds coming off each junction point, or you can have the primitive arrangement on the left-hand side, also called the plumber's nightmare, where each junction has got 6 bonds coming off it, 6 branches coming off it, and that's really easy to understand in 3D space, because those 6 bonds all sitting at right angles to each other just end up with this very easy to understand arrangement. 2 separate spaces, each permeating 3D matter. If you think about what's happening in the geometry of these different spaces, though, you can think of each of these bicontinuous phases as being a tunnel network. But they're tunnel networks in which the radius of the tunnel varies depending on where you are in the system. And what Gert did in his PhD work was map out the distribution of radius sizes as you move around these systems. The gyroid is on the right, and it has quite a narrow range of tunnel radii. The diamond in the middle has got a bit of a broader range, and the primitive or plumber's nightmare, the easy to visualize system, actually it's got a really broad range of diameter to accommodate. And it's really challenging for a hard particle system to achieve this range of pore sizes, of radius sizes, because a hard particle system has only got entropy to play with, and it's trying to fill space, it's trying to avoid gaps, and having rigid hard particles achieve such a broad range of pore sizes is really quite challenging. Experimentally, the gyroid phase is much more often seen than the diamond or the primitive. You look at elastic models of the 3 phases, then the curvature elasticities are virtually identical for all 3. But the big difference is the range of pore sizes that are entrained in each of the 3 arrangements, and that's almost certainly why the gyroid is what is seen most in nature. We tried to achieve the diamond phase by perturbing our hard pair systems. We couldn't do it by just changing the pairs themselves. We needed some way to achieve this broader distribution of pore sizes. And we did that by trying to add a second species, hard spheres. We tried adding spheres of different sorts, different sizes. And particularly, we thought that adding spheres whose radius was similar to the the radius characterizing the blunt end of the pairs. We thought that they would pack very well, and then the spheres would likely aggregate in order to fill some of the holes that would otherwise appear because of the broader distribution of radii. It's kind of equivalent to experimentally how the diamond structure is stabilized in block copolymer systems. They do that by usually adding some free oligomer, and the free oligomer is thought to aggregate or preferentially reside in a fairly regular way, and essentially pack out the system in ways that the block copolymer can't when it's there on its own. Now, so here's a simulation. This is the simulation outcome when we did include the right kinds of spheres in with our hard pair system, and indeed it did give the diamond arrangement that we were after, which is a great success. This is the first observation of a freely forming diamond structure from molecular dynamic simulation of hard particles, published that in 2018. But what was wrong was our supposition as to the mechanism by which the presence of the spheres encouraged the pairs to adopt a diamond arrangement instead of a gyroid arrangement. Our hypothecated mechanism, which was that the spheres would aggregate around the blunt ends of the pairs, was completely wrong. Here's the evidence for this. In the isotropic phase, so this is a heat map, the yellow areas show where the spheres are most likely to be seen around the pairs. Now, in the isotropic phase, we get a kind of broad smeared out yellow region around the flanks of the pairs, which was okay. Into the isotropic phase, I guess the spheres can go where they want to. In the diamond phase, we were expecting to see lots of spheres packed around the blunt end because they're the same radius. You'd think that the effective packing would be best there, but in fact, exactly the opposite happens. In fact, we get an increased concentration of spheres in this flank region. So it's not simple, straightforward efficiency of packing, which is going on here. We look in more detail to see where the spheres are most likely to reside. In respect of the minimal surface, the dividing surface in the diamond network, which is, if you like, the center point of the interdigitation of a bilayer. If you have a bilayer, then the minimal surface is the line that goes down the center of it. If we look at where the spheres sit with respect to that minimal surface, actually they're very much the maximum occurrence coincides with that minimal surface, and then the spheres aren't absolutely tied to that. It could drift one way or the other, but they're symmetrically about it, and it's the most likely point. And then we look at the location of the spheres with respect to the Gaussian curvature of that minimal surface. The Gaussian curvature varies as you move through the diamond network, and we get a really strong concentration of the spheres where the Gaussian curvature, modulus of the Gaussian curvature is highest. So where the minimal surface is most saddle-shaped, that is where the spheres are sitting. So they're sitting on the surface, on the minimal surface, where it's most saddle-shaped. They're not sitting at the blunt ends of the pairs, which is a long way away from the minimal surface. So adding the spheres opens up this new symmetry going from the gyroid arrangement to the diamond arrangement, but by a previously unseen route, and we certainly weren't expecting this to come in. We were not getting out what we had put in. We put in some spherical particles to add as fillers, if you like. They have filled, but not in an expected place, and they changed the symmetry of the of the superstructure which is formed. These things are interesting. These bicontinuous phases formed by these hard particles. Experimental gyroid phases are usually seen in between hexagonal and lamellar arrangements, whereas we were seeing gyroids between nematic and smectic. No sign of hexagonal order in any of these systems. And this was all completely unpredictable when we first did it. You saw this picture from Roald Dulland's. Twist bend pneumatic were predicted in the early 2000s by Dozoff. This is where the bananas predicted to wind in helices around some axis. In the same paper, Dozoff predicted the splay bend and hypothecated this arrangement, which is what Dulland has just seen, and simulations by Murray and Dijkstra. But bananas are not the only fruit. We're talking about pears here, and the modulated director that those are predicted in bananas is actually also seen in pear arrangements if you introduce local polarity. Additionally, essentially there's a splay bend coupling because of the packing of the particles. Because our pairs are pairs and are not pieces of cake, there's actually a third dimension to these systems, which isn't there in Dulland's system, as I said, because his bananas are not tapered. This was looked at by Jonathan Selinger, really nice little paper, which I was surprised wasn't included as a reference in Dulland's science paper. He looked at some continuum theory, considering some Dozoff-like ideas, and he looked at the coupling between local polarity and splay by adding essentially an additional term to a Level-Lasher-like model. And by cranking up this C term, he found that the pneumatic order became unstable to 3D modulated phases. So a periodic splay bend phase, I won't call it splay bend pneumatic because this is splay bend in 3 dimensions rather than just in 1 dimension. But we think that what we have observed in our hard pairs is akin to this. It's a it's a splay bend phase, and that's where it comes from. And that's why the phase behavior is so different from what is seen in block copolymer systems. Anyway, so moving from a uniaxial to a polar particle shape, we get some expected phases like the bilayer smectic. We also get some unexpected ones like the gyroid and the diamond. All of that has come from changing the symmetry of the particle that we've introduced. If we're just using ellipsoids, we wouldn't see any of that stuff. So to form bicontinuous phases, we find you need to have systems which form bilayers, are happy to adopt Gaussian curvatures, and are able to accommodate this distribution of pore width that was looked into by the theory of Gert Schroeder. But also this ability to manifest local polar splay coupling, and that's really where the particle symmetry comes in. It's a necessity. But rather interesting, these are orientationally isotropic bicontinuous structures. We've got a larger length scale symmetry, a supramolecular symmetry of either gyroid-like or diamond-like. They seem to come about by following the ideas of Selinger. It's that polar splay coupling which actually stabilizes them or induces them. I'm going to change gear now and change the color of my background. I'm going to go black, and we're going to start looking at self-assembly. I was keen that I include some self-assembly in the talk. And this is a different set of systems we've been looking at, but again, that same kind of level of coarse graining. We've been looking at well, what in the UK we call Smarties. I guess in the US it would be the M&Ms, disk-like objects, disk-like variants of the Gay-Byrne interaction potential. We have disks, and we can have them attract each other face-to-face generally more strongly than they do edge-to-edge. So the discostic variant of the Gay-Byrne particle. Because of face-to-face is the most stable arrangement, at low concentration, these things will tend to stack and therefore give us chromonic type behaviors. We're just doing absolutely basic MD simulation on these objects. No tricks, no biases, no accelerations or rare event monitoring. That's because we don't want to bias the outcome. And in fact, the kinetics of the growth of these objects is a talk or two on its own, and which I won't be able to go into here. The high concentration bulk behavior of discotic gay band is really well known, determined in the 1990s. Martin Bates, now at York, this was his PhD material done with Geoffrey Luckhurst in the early 90s. Essentially at low, well, at high temperature, you get an isotropic phase. You cool that down, you get a discotic nematic, which is depicted on the left. Cool it down further, and you get a hexagonal columnar phase. That's all fine. This is a dense phase, a high concentration phase. What we have done is take the same model, but rather than run it in a dense phase, try simulating it at much lower concentrations. When you do that, at high temperatures, you have an isotropic arrangement. You know, discs flying around all over the place, not doing very much. If you get them down to just the right temperature, though, and the different lines here correspond to different shapes of particles, different aspect ratios of particles. At a certain temperature, that vapor will aggregate, and it aggregates into a single large object, typically encompassing 90 or 95% of the particles in a single aggregate. That aggregate, as indicated by the symbols, might be a twisted fiber or might be a straight fiber. And we've done this again and again and again. It's highly reproducible. If we change the thickness of the discs or change the strength of the attraction, then for strong attractions on the left-hand side, we get straight fibers forming. If we weaken face-to-face interaction, we get more and more twisted arrangements, and the object that's formed for a fixed number of particles is a bit shorter and fatter if we weaken the face-to-face interaction. This happens really reproducibly. Now I can show you it happen. So it's a video playing along here. Formation of one of these fibers happens by a kind of it's got two clear stages. In the video, I'm only showing you the discs which are part of an aggregate which involves at least 4 particles. This is a run which, well, the video started part of the way through the run. In the early phases of the aggregation, though, we get the kind of things which are shown here on the left here. We get lots of monomers, we get some threads of those monomers. Occasionally those threads will come together as 2 threads. But even more occasionally, we'll get a triplet forming. These arrangements make and break and make and break, form and unform for quite a long time. Eventually, one of them aggregates to something larger, a 7-thread twisted core. And once that 7-thread twisted core has formed, then that reversibility that we get in the pre-assembly phase of the growth goes away, and that 7-thread twisted core provides a template which doesn't fundamentally change its shape, and the object keeps on growing and growing and growing. We end up with a defect-free, beautiful twisted fiber coming out. What happens if there are more discs? If there are more discs, then the object is going to keep on growing longitudinally and radially. But there's a bit of a problem if these twisted objects grow radially, and that is the fact that there is a growing strain energy in these systems. The strain energy of these twisted arrangements grows really quickly with radius. Continuum theory by Greg Grayson says that radial strain grows as the 4th power of the radius. What does that mean? Well, it means that as the radius grows, something's got to change. Either the object has got to stop growing because it's reached its, because the rate of aggregation and the rate of particles flying off, when we're looking at it will balance each other out and it'll stop growing, or alternatively it needs to find an alternative arrangement. And this paper by Hall and Grayson from that map a few years ago predicts that at a certain radius, the twisted cylindrical fiber becomes unstable with respect to a twisted tape. And rather than being characterized by a single radius, it'll split out into something which has got a width W0 and a thickness T0. So the overall cross-sectional area is conserved, but you get a discontinuous change in shape of the object as the radius grows. We're seeing this is characterized as a frustration effect. The growing frustration associated with adding increasingly twisted fibers around this twisted fiber, because each shell, if you like, of twisted fibers is twisted even further and twisted even further, and they get less and less happy. And that causes these things to be unstable with respect to the twisted tape, according to Grayson's theory. If we do simulations of these objects, what we've got to do is get a bigger computer and throw in 10 times as many particles and see what happens, and presumably we'll see the same thing. So that's what we've tried. Looking at 20,000 particles, excuse me, instead of just 600. And I'm not showing all the particles here. I'm only showing the particles in the aggregate, and most of them I'm just characterizing as white lines, but those which are going to form a central band, and here the image in the bottom left is looking longitudinally along the finished structure. Only ones in the central band are being shown in the video. You can see that they're slowly twisted with respect to each other. You can see that the overall fiber is twisted from the white lines. But this band of central threads, the white one in the middle is straight. The red and the green ones are equivalent, slightly skew with respect to that. Then the dark blue and the light blue are slightly skew with respect to that. This object is growing and growing. The color particles you can see are colored by the given the color they're going to need at the end. So you can see, sorry, at the end of the simulation, or corresponding to the thread that they're eventually going to join. So you can see that some of them look like they're in the wrong place. That's because those particles within the MD simulation are going to leave that location and are going to go somewhere else. Still got a twisted fiber, it's getting pretty big. Growing and growing, growing and growing. We've got 5 times as many particles as we had in the original fiber simulations, but eventually this thing is going to get too big. Its radius is going to force it to do something else, and there it goes. Rather than being a twisted fiber, the entire thing has untwisted en masse. It hasn't done what Hall and Grayson said it would do. It hasn't formed a tape. Instead, it said, yeah, I am getting frustrated by being twisted, but the kinetically accessible thing for this system to do is to straighten up, and it straightens up by completely untwisting rather than by breaking its threads and remaking alternative ones. Okay, let's step back a little bit. We get spontaneous structural chirality in these self-assembled objects. We get that because these fibers are made up of threads. Those threads would like to pack hexagonally with one another, but they would also like to interdigitate with each other. But you can't achieve both hexagonal packing and interdigitation of 3 neighboring threads. They interdigitate slightly. By interdigitating slightly, they manage to get slightly closer to each other. They can pack more efficiently. So the locations of the threads get to within approximately 0.95 the disk diameter with each other. If they were packing hexagonally, then it would be 1.0. They'd be so equivalent to tins on a shelf. That slight interdigitation gives them a propeller motif, and if you stack propellers on top of each other, then you end up with this twisted fiber. This picture here, this with the blue guy in the middle, that's not from our work. That's theoretical work from Chakrabarty, which actually came before our simulations. So this structure was predicted as being the most efficient packing for Smarty-like objects, for the disc-shaped objects. Our MD simulations have found this. If we make the object grow bigger, then it leaves this this motif behind. The frustration causes the fiber to untwist, and the spontaneous chirality goes away. Another point is that size really matters in these systems. The size of the object, particularly when we've got these frustration effects, controls the morphology that is observed. So in the pre-assembly phase, we don't have any twist. For the for the strong phase-phase interactions, where, if you like, the threads aren't very elastic, they're quite rigid, and that rigidity causes them to want to grow straight all the time, and then end up with the large object. If we have the weaker face-to-face interactions, then we end up with the twisted 7-core 7-fiber core, which then templates a larger twisted fiber and a larger twisted fiber, but eventually those twisted fibers, as the radii grow, then they get pulled straight. So the favored morphology can change discontinuously with the aggregate size. We get the spontaneous twist, but only for a certain range of object sizes. And the changes in the symmetry of the object are controlled by continuum behaviors. We're doing molecular simulations, particle-based simulations, but we're definitely accessing continuum-based behaviors when we get this frustration-driven, usually discontinuous changes in the shape and indeed the thermodynamic branch that the observed object is sitting on. So that's what happens with disks on their own. We can also look at mixes of disks and spheres. I'll do this bit fairly quickly. We introduce an amphiphilic interaction around the disk, which attracts some spheres, and in that type of situation, these are amphiphilic, so unsurprisingly they form bilayer-like arrangements. Here the red spheres here show the location of the attractive region on the disk which the spheres are attracted to. We get these high order sandwich-like arrangements. We have a layer of spheres between threads of disks. But as these objects grow, again, we get twisted structures coming out. This is a typical final arrangement in one of these systems. We've got a sandwich of spheres between threads of disks. Those threads of disks, each of them follows a bit of a helix, and there's a really long, really huge pitch emerging from these systems. The pitches are typically between 50 and 100 particle sizes. All we're putting in is the particles, getting a really large emergent length scale and clearly a twisted object, as well as the longitudinal twist. In fact, the threads in the two leaflets are slightly skew with respect to each other. So the red lines are the threads on one side of the bilayer sheet. The brown lines are the threads on the other side of the sheet. You can see they're slightly skewed with respect to each other by between 10 and 20 degrees. We can do a similar simulation with weaker face-to-face interactions. When we do that, we get one twisted bilayer, and then which is the mother twisted bilayer, and then we get a second one that attaches to it. When the second one attaches to the first one stops growing, and the second one takes on all the material. The number of particles in the bigger leaflet remains fixed. The number of particles in the smaller leaflet grows until they become the same size as each other, and we end up with this beautiful double bilayer. All we've got here are spheres and Smarties, no chiral interactions, and we're seeing a really hierarchical self-assembly. The disk and spheres are our base units. The threads of disks are our first level assembly. Clusters or bilayers of disks and threads and spheres are our second level assembly. But when we have two bilayers coming together, then that's our third generation of hierarchy. A different system with a smaller head group, a smaller attractive region. Here we get a line of spheres going down the center of a multi-threaded object. That's another view of the same thing. You can see the little sphere sitting in the middle and the threads wrapping around. No chiral interactions here. This is all driven by packing and attractive interactions. Run the simulation on a bit longer, another one of these objects form, and they then start wrapping around each other. So a second level of chirality. Here comes a third one coming along, and that wraps around them again. So we've got the pitch of the individual threads around their core, and then we have the cores themselves on an even longer length scale. Keep on running the simulation. Are there some more threads going to come and join on? No, something changes. The thing that changes is that rather than having these these helical threads wrapped around one another, there's a morphological change, and rather than threads, you can now see from the red spheres here, sorry, I'm changing color scheme here, that we're now getting a sheet of spheres and another sheet of spheres, and this has gone a morphological change from a circular cross-section object of multiple threads into a double bilayer arrangement, and that double bilayer arrangement then becomes the dominant structure. And here we have observed what Hall and Grayson predicted. We've seen a change from a circular cross-section to a thread-like one, and this is experimental and theoretical images from their work. So this is frustration driving a change in the twist. None of this have we put in, if you like. None of this would be apparent or readily predictable from the symmetry of the objects which are in the simulation. And in fact, these disk sphere systems are incredibly rich in terms of the range of twisted structures that they throw up. I can talk about each one of these for well over an hour. We get this guy up here is a double helix. This guy up here is a bilayer tube, all spontaneously self-assembled from the same basic units. The twisted ribbon bilayer is interesting, very interesting. They've got a pitch. There's a skewness between the leaflet threads. There's clear twist there, but what's the origin of the twist? Are these just indicators of it, or are they the cause? And we really want to know that because we like to gain control over it. For the completed ribbons, we can measure the twist. In fact, there are two pitches, one longitudinal and one orthogonal. We can measure this by looking at the helices trapped out by the threads, or we can alternatively fit to the approximately a helicoid of the spheres in the central region. These pitch values, yeah, like I say, they're between 80 and 100 particle sizes. And we can look at how the pitch changes with the ribbon size. Generally, as the object grows, the pitch length increases. As I say, the twisted bilayer untwists slightly. But the extent to which that happens depends on how big the hotspot is. For small hotspots, we get more untwisting than we do for large hotspots of size 50 or so. So it's showing the pitch either as a function of the number of threads or as a function of the number of particles in the system. And this untwisting is, again, a frustration effect. As the width of the ribbon grows, the threads that join onto it are being more helical and therefore are energetically less happy. And that's what straightens the bilayer or increases the pitch length as the object grows, particularly for the smaller systems. What's achieving the twist in the first place? Where does it derive from? Ultimately, it comes down to the particles. We can look at the statistics of where the particles sit with respect to the disks. In fact, they don't sit at the edge, directly at the edge of the disk. They tend to sit a bit above and a bit below it. That's where the particles sit. And here they're color coded by the energy that they have. And it's these object scale properties which ultimately control or bring about the behavior. I guess that has to be the case because all we're putting in are particle-particle interactions. And ultimately, we've done is some relatively simple geometrical analysis in order to really determine what the origin of the twist in these systems are. And this is work that's been done by Savetta Matsumoto from Georgia Tech. For this, we've put together an idealized bilayer setup. So we've taken a naive planar packing arrangement, squashed that down in an affine transformation. That's given us a single sheet of interdigitated disks. We've then replicated that on the other side, and we put in a layer of interdigitated spheres in between them, and then minimized the energy of this thing by having put in all the interactions, minimized it with respect to two key variables, one of which is a pitch length, and one of which is the layer offset for how far the bilayers are displaced with respect to each other. And when we do that, then sure enough, this geometrical model predicts for our standard particle size and hotspot size an optimal pitch. The twisted arrangement is more efficiently packed and has got a lower energy than the straight one, and we get an optimal pitch of about 48 disk units, and in simulation we observe 50. So we're rather delighted by that calculation. Don't want to make the geometrical model any more complicated. Also, the model predicts there's not really that much dependence on the size of the hotspot. So the twist in these bilayer systems really originates from the optimal packing. It manifests itself not at the particle level, it manifests itself at length scales between 50 and 100 times larger. The twist that we get from this optimal packing is there for a certain size of object, but as the objects grow because of internal strains and frustration effects, we will see changes. We'll see the overall bilayer untwisting a little bit, particularly for small h values. And ultimately, we might then see something else happening as the object gets even larger. They can only grow laterally to a certain extent before frustration effects will dominate. I've just said that. I want to have a couple of minutes just about a surface system, which is kind of fun. Which, am I okay? Do you want me to stop, Hallam, or should I say a little bit about this?
Well, we are running out of time. If you can just go through it in a couple of minutes.
I'll do this in 2 slides. You all know about elastic constants. K1, K2, K3, 3, and then we have the saddle splay elastic constant, which is usually ignored or dismissed as being a surface effect. I won't show you that. Like Margaret, I did my PhD in the theory group in Bristol, where Sir Charles Frank was my first ever talk, which was about the Frank constants, which was tricky. We normally kind of ignore the KT4 term because it can integrate out as a surface term, and then we kind of ignore it, and Monty Python's foot comes down. And it kind of renders KT4 virtually immeasurable, but it's there in the maths, it's definitely there. What this relates to is some experimental work done at UPenn in Xu Yang's group, using SU8 and photomasking that. You end up with a surface which has got these circular things on it. These circular patches induce alignment in plane, whereas the base induces alignment orthogonal. If you look at the resulting optimizing microscopy pictures, the results of these things look a bit like Maltese crosses, but they're slightly twisted. That slight twist comes about because of K24. Some are left-handed, some are right-handed. These are kind of individual posts. They're pinwheel structures. That's one arrangement. Another thing that is seen sometimes is boojums. If you heat it up and cool it down, sometimes you get pinwheels, sometimes you get boojums. You can explain that work by Tim Atherton at Tufts Group, at Tufts University. You can see the pinwheel being stabilized at a continuum level. You can see the boojum being stabilized at a continuum level, only if you include K24 in the calculation. That's kind of fun. If we look at this alternative system of polos, where again it's the SU8, so the tops of these things want planar alignment, but the holes going down to the base, then you get orthogonal alignment, then you get something really strange. This is the experimental picture, and you get a polar director structure. So what's happening on the right is clearly different from what's happening on the left. And that's due to saddle splay effects. Again, if we use those same values for saddle splay, then this is the director structure that's coming out. And again, this kind of 2 bright areas on the top right and the bottom right lightened up, because we've got kind of 45-degree angle arrangements on the right-hand side, but left to right arrangements on the left-hand side. We've got a polar arrangement. It's motivated by K24, driven by K24 effects. And because we've got a polar arrangement, actually there are 4 possibilities. Those 2 things, bright regions can point up or down or left or right. Got a pattern level polarization. Actually, we can also get them to point at the 45-degree angles as well, and we can achieve switching by having interleaved contacts on the top and bottom. Top ones do north to south, and the bottom ones do east to west. And so we get multi-stable arrangement. In fact, an octastable device where we can switch between the different arrangements just using a driving field. I won't show you the video because I haven't got enough time, but we can dynamically switch between these polar arrangements. In these systems, the liquid crystal, the uniaxial everywhere, there is polarity. That polarity is on the pattern scaling. So it's a really nice, really interesting system. Completely emergent symmetry. The polarity is driven by incorporation or utilization of K24 terms. Right. Sorry, Hallam. I shall stop. I'll put up my thank you slide. There you go. There's lots of people that have done lots of good work. Sorry, Hallam. I'll stop you. Got any time for questions?
Right. Thanks very much, Doug, for a fascinating talk on many different types of self-assembly and some equally fascinating liquid crystal work at the very end. Okay, so we are now open for questions. If you have a question, comment, praise, criticism, please raise the little blue hand. If you don't know how to raise the little blue hand, just shout. Okay, so who wants to be first? Come on, who wants to be first? Hello? Oh, I see Margarita wants to ask a question. Margarita, fire off. Margarita? Can you guys hear me?
I forgot to unmute me. God.
Okay, yeah, we can hear you now.
I'll only ask a very quick question because there were quite a few, especially this last part that you went too quickly. So seems very interesting, but you lost me. Yeah. But anyway, about the fibers and about your packing arguments, there's something that doesn't sound quite right. I mean, you can use the packing arguments if you have a very dense system. Your system to make the fibers has to be very dilute. So can you explain that to me? I'm probably being very daft, but
so the aggregate that forms is very high, very high density, as you say. It's closer than close packed. It's not a crystal; it's a finite size object. But the fibers that form are.
No, but the fibers have to be in a dilute system, otherwise you would find something else, right? They're not, I mean, you're talking about one fiber. So overall, what is the concentration? What is your packing fraction?
Okay, the overall concentration is very low, it's about 0.
Yes, that's what I was saying. So,
these things are aggregating out of a very low concentration solution.
Right.
And that's what real fiber systems do.
Sure, but then it cannot be just a packing argument. I mean, what makes the fibers make, fibers? It's got to be the attractions.
The aggregation is controlled by the attractions. Yeah, they wouldn't aggregate if it weren't for the attractions. But the object in which that they aggregate into is controlled by shape. once they've aggregated, then the choice of arrangement that they adopt is controlled by their shape, and therefore that's when packing comes in. So you need attractions to aggregate. Once they've aggregated, the arrangements are then controlled by packing arrangements.
I think it's clear now. Thank you.
Right, thank you. Any more questions? Who has questions now? Comments, praise, criticisms? Doug, I have one question about the twisted bilayers you mentioned.
Mm-hmm.
Yeah, just remind me, what's the model there? Is it amphiphilic discs?
Yes. So each disc around its rim, there's a hotspot region. Say 20% of its rim will be attracted to the spheres. All right.
So it's amphiphilic discs and spheres.
Yeah.
And the sphere is attractive all around.
Yeah. The spheres are bog standard Lennard-Jones.
All right.
And the disc interactions are just normal gay burn. So the only fancy bit in it is that amphiphilic disc to sphere interaction. We'd expect amphiphilic behavior to give you bilayers, but because the sheets of those bilayers are made up of threads, that's why we start getting these twisted arrangements.
Okay. Now, coming back to the threads, you say that they're chiral, right? They twist around this central axis, but well, some fibers will presumably twist one way, and other fibers will twist the other way.
Oh, absolutely. Yeah. We get half our systems doing one thing, doing left-handed, half doing right-handed. That's no problem with that. In the simulation, we try to only allow. Well, we try to be careful enough that only one large object forms.
Okay.
Interesting things happen when you get different-handed objects forming, and in fact, the interaction between a right-handed double helix and a left-handed double helix is something that we see all the time, and sometimes they merge with each other as well. So we get behaviors on higher length scales as well.
And lastly, about this K24 work, is it now completed, or are you still pursuing it further?
Yeah, that's completed. I'll show the switching video just for fun. So this is a system which is currently pointed towards the left. We apply a vertical field, then the chevrons point up to the right, up to the top, and then now we've locked in plus half defects. So we warm it up and cool it down. We get a really nice, elegant system. But you can rotate these things left-handed, right-handed, any amount that you want by applying the field. You could impose an overall helix by gradually wrapping around this, gradually applying 45-degree switches at the bottom surface. All the experimental work was done in UPenn. I never went there. I never went until last December when I got to see the lab where all the work had been done. And I got involved because of a discussion that this exotic thing that we used to have. It was a conference. Somebody tapped me on the shoulder, poster session, and showed me these pictures, which made no sense at all. This polar arrangement. There's nothing polar in the system. But I didn't understand it until we then did the theory with Tim and I. Yeah, my contribution was to sit at the end of a Skype call and say, try doing this experiment, try doing that experiment. And the clever people in UPenn managed to do it.
Okay, thank you. Are there any more questions, comments, praise, criticisms? I don't see any little blue hands. So let us thank you, Doug, again. Thanks very much for this fascinating talk. We'll be in touch.
We will.
And next week we have a seminar by Alenka Mertel from the Josef Stefan Institute in Ljubljana, Slovenia, who will tell us about her ferroelectric pneumatic phases. And you're all welcome to attend if you're in the mood and if you have the time. So thanks again to all. Bye-bye. See you next week.